Alright guys, welcome back, and today we're going to be going over multiplying binomials. And so for a think slash warm up, we know how to distribute something like 2x times 5x minus 2. We would just multiply both those things by 2x. Now think about how we might multiply two binomials. So binomials are a term or an expression that has two terms in it, right? So that has 2 and that one has 2. So how would we multiply something like this? And my hint is to think of 2x plus 1 as just a single number, right? Because if we knew what x was, that would be a single number, right? If x was 2, then 2 times 2 would be 4, plus 1 would be 5, and it would be 5 times that. So really what we can do is we can treat this all as one thing, and we can multiply it by 5x, and then we can multiply it by negative 2. And we will get into an example of that. So multiply the two binomials. The first thing I'm going to do is I can do x minus 7 times x, which I can write as x times x minus 7. And then I could do the whole quantity x minus 7 times positive 6, which I can rewrite as 6 times x minus 7. And now we know what to do, right? X times x is x squared. X times minus 7 is minus 7x. 6 times x is positive 6x. And 6 times negative 7 is going to be negative 42. Yeah. So, and now we have two like terms in the middle, right? Negative 7x plus 6x. If we have negative 7 of something and we add 6 of something, we should have minus 1 of that something left, so minus 1x minus 42. And minus 1x, if we want to write that just a little nicer, minus 1x is the same thing as just minus x, right? And there's a couple things to take note of and see if you see the pattern continuing. We have minus 1x here. Does that have any relation to this minus 7 and this plus 6? And then we have a negative 42 here, and does that have any relation to this minus 7 and plus 6? Just keep thinking about that as we keep going. And so if you want to write something out like this, that's totally fine. But I also have another way to do it, which gets you the same result. So what I do is distributing is the same thing as saying, well, let me do 3x times that, and then 3x times that, and then I do the same thing for the other one. That one has to be multiplied by that, and that one has to be multiplied by that. As long as you hit everything, you've distributed properly. So let's do that. We can do 3x times 2x. 3 times 2 is 6, and then x times x is x squared. And then we can do 3x times negative 3. That's going to be minus 9x. And then we can do negative 5 times 2x, which is going to be minus 10x. And then we can do negative 5 times negative 3. Negative times a negative is a positive. That'll turn to plus 15. And then minus 9x minus 10x, we can combine like terms. That will be minus 19x plus 15. And again, take note, look at this negative 19. Does that have anything to do with, well, these middle terms are a little wonky because we have positive 2 times we have 2 times negative 5 and 3 times negative 3, but there is a relation there that's easier to see with ones like this one. So minus 1, when you add these two last numbers, you get negative 1, and then when you multiply them, you get negative 42. So then here, I thought I'd throw this one in here. 2x plus 1 squared. This is the mistake that you probably see most in math. A lot of people will want to write, well, that's 2x squared plus 1 squared, right? They're thinking just throw that in there. But remember, that's not true. Those are not the same thing. Remember what squared means? Squared means something times itself, right? So that's what it means when we have a binomial squared. And now we can do this. 2x times 2x is 4x squared. 2x times 1 is plus 2x. 1 times 2x is also 2x. And then 1 times 1 is just 1. Combine the two like terms in the middle, and we're going to get 4x squared. 2x plus 2x is plus 4x. And then we have that plus 1. So algebra tiles are just a visual representation of an algebraic expression. So for example, and this might be confusing at first, but then I think once we get into some examples, it'll be a little more clear. If I said this thing was x squared, and this thing was x squared, or let's just say x actually, or let's do xy, that'll be fun. If this thing's xy and this thing's xy, and let's just say these are 1, these are worth 1, then the expression that this represents would be 2xy plus 4, right? We have 2 of these xy's and then we have 4 1's, which is the same thing as 2xy plus 4. So if we go here, what expression is represented by the algebra tiles? If we do this one, we have a single y squared, so 1y squared or just y squared. And then we have 3 of these xy's, right? And so that's all that one is. And now for this one, we have 2 y squareds, and then we also have 2 x squareds. And that's the answer for that one. And a quick note, this looks like a square because x squared, this side would be x times x, right? Which would be the same side length, which would make it a square, and then the area would be x squared. Just something to take note of. So, similar to algebra tiles, we can use area models to help us distribute, which can help us multiply binomials. Let's think about our previous example of 13 times 7. So, if we had a rectangle that was 7 by 13, and I asked you to find the area, you would just multiply 7 times 13, right? And 7 times 13, 7 times 10 is 70. And then 7 times 3 is 21. Add them together, you'll get 91. So you know that the area of this would be 91 units squared, whatever the units are. (91 units squared). We'll notice when we multiply them, right? Because that's what we did. The multiplication is the area of this rectangle. So we're going to do the same thing with binomials. If we said arbitrarily, if this length right here was x, and this one was also x, it's not to scale, otherwise it would be a square, right? We're just saying that. And then we said, well, this one is right here. I'll color code it this way. So let's say this length is x. Well, and then we also want to do plus 1. And we said that length is 1. Now we want x plus 3 if we said this length is x. And then we said this length is 3. Aren't we multiplying those binomials together? So if we're multiplying those binomials together, these areas added all up should be this total area of this huge rectangle all the way around, which would give us the answer, right? 13 times 7 is 91. And so this area gets us what 13 times 7 is. And so if we're multiplying x plus 1 and x plus 3, this area should give us the end result, right? So let's just compute that? Well, we can do it rectangle by rectangle. So we know x times x is x squared. And then we know x times 1 is x. And then x times 3 is 3x. And then the last one here, 3 times 1 is going to be positive 3. And now we can put all of that together. So we have this x squared up top. Well, then notice we have an x, a 1x, and a 3x. If we add those together, we'll get 4x. And then at the end, we also have 3. So here's our answer, right? If we multiply these two binomials, x plus 1 times x plus 3, this is what we get, right? This is another way of distributing. So here, let's fill in these area models. We know 2z times z is going to be 2z squared. And then we have 3 times z, which is just 3z. 2z times negative 1 is going to be negative 2z. And then negative 1 times 3 is going to be negative 3. And then what that tells us is that 2z plus 3, what we have on the top there, multiplied by, because we're doing an area, z minus 1 is going to equal this area, which this area is 2z squared. And then notice we have a 3z and a minus 2z, which is going to end up to just be plus 1z or plus z. And then at the end, we have a negative 3. Now for this one, we have to find some missing parts, right? So we have to find what goes here and what goes here, and then also what goes in the two boxes. How would we find something that goes there? Well, we know that whatever goes here times negative 3 is negative 12g. So if you really wanted to figure it out, you could do negative 12g divided by negative 3. But I think that it would just be better for us to just think about it, right? What times negative 3 is going to get us negative 12g? Well, it should be positive, right, in order to get a negative. So whatever it is, it's positive. And then what times 3 is 12? That's going to be 4. Oh, and then we're going to need a g there too, right, to get that g. So up here, we should have 4g. And we can check that going backwards, right? If we do 4g times negative 3, we get negative 12g. So it worked out. Now let's do that same thing for this one. Except now we have a little more information, right? Or now we have the same information. We have 4g and we have 8g squared. So what times 4g gets us 8g squared? 8g squared. Well, so first, what times 4 is going to give us 8? And that's going to be positive 2. And then we have a g, but we have g squared here. So we're going to need another g. And so 2g times 4g is going to be 8g squared. That works out. And then we can just fill in the rest like we have been. 2g times negative 5 is going to be negative 10g. And then negative 3 times negative 5 is going to be a positive 15. And so then if we were to write this out, what this tells us is that the top one there, 4g minus 5 times 2g minus 3 equals, and then we have our top, our 8g squared minus 10g minus 12g together is minus 22g. And then we have a plus 15 at the end. And that is completing those area models and writing the equations, the algebraic expressions from them.